I'm going to draw two pictures here. First picture, we've got object number one, call it a car, call it a ball, it doesn't matter. Object number one is moving to the right at 10 meters per second. Object number two is at rest. It's not moving. Now you can imagine after they collide, they're both going to go off to the right. Let's assume that they stick together. There's Velcro on it or whatever it is that causes them to stick together. They both go off together after the collision. Although that doesn't really matter. Okay? If they went off separately, the same analysis would apply. Now let's take a look at another picture where we have object number one at rest, right here, 0 meters per second, and we have object number two that's moving up this way at, let's say, 15 meters per second. Again, we're going to say that they stick together, and after the collision, they head off to the north as one object, slower than 15 meters per second, right? Because the mass is about double what it was. How would we analyze both of these problems? What's the technique that we use to analyze the first problem there, Adam? Yeah, it's conservation of momentum, right? Pi equals Pf. M1 V1I plus M2 V2I, and so on. Okay, so let's set that up here. We won't calculate it because we don't have numbers for mass here, but we'll set it up here. Pi equals Pf. We're going to say M1 V1I plus M2 V2I equals, because they stick together, we're going to say MVF. Now, if they didn't stick together, we just say M1 V1F plus M2 V2F. Let's do the same thing over here. Again, let's say Pi equals Pf. Let's say M1 V1I plus M2 V2I equals MVF. Now, let's go through this here, okay? Let's go through this and take a look at a few numbers. Again, we're not going to calculate it, but take a look at a few numbers here. M1 doesn't matter what it is. V1I is what? What's the value of V1I right there? 10 meters per second. M2 is, doesn't matter what it is. What's V2I? 0 meters per second, right? And M is the combined mass. VF is probably what we'd solve for there, right? VF. Okay, let's go to the next one. M1, don't know, V1I, sorry, is 0, so that disappears. M2 is whatever. V2I is 15. Combined mass times VF, solve for VF there. Again, it works out to be whatever. So far, so good? There's nothing new here yet, is there? Okay, this is what we've done for a couple weeks before the break, right? Just straight conservation of momentum. Or here's a problem where two cars collide, or two objects collide on the x-axis, and here's another one where two objects collide on the y-axis. Yep. So we're assuming, yeah, that's a good question actually, Chase. We're not looking at this from the side, we're looking at it from above. So object number two isn't going up into the air. We're just looking at it from above where it's all on a horizontal surface. So gravity, although it does act on everything, it's on another axis. And gravity's pulling down, but let's say there's ice, so no friction to take energy away from it. Are we good at this? Yeah, I don't think this is crazy hard, what we've done here thus far. Let's draw another picture, though, a third one. Object number one is moving to the right at 10 meters per second. Looks familiar so far, right? Let's make object number two moving upwards at 15 meters per second. When they collide, at this point, they're going to head off as one object after the collision. They stick together. Well, how do we analyze this? What you see down there at the bottom in green is exactly the same as what you see up there in red. It's two problems, each of which are a conservation of momentum problem. Okay, the first problem up here that we drew in blue, we said Pi equals Pf for an object traveling on the x-axis, hitting another object at rest on the x-axis. What do we have down here? Well, we have an object traveling on the x-axis, hitting another object that is, well, it's traveling on the y-axis, but as far as the x-axis is concerned, how fast is that moving? 0, right? So part of that problem is just like this. But part of that problem is also like this, because object number two is moving upwards to the north or whatever it is. So all we're going to do when we go to solve this problem is to break it up into two components. an x component and a y component. For the x component, we'll do this. For the y component, we'll do this. Now, let's take a look at our setup here again from the perspective of the green diagram at the bottom, not the blue one. Remember, when we were looking at the blue diagrams, we crossed off some things because it was 0, right? Let's see what that looks like when we look at the bottom problem here, the green one. M1, don't know what it is. What's V1I there? Again, we're not paying attention to what's up here now. Okay, we're paying attention to what's down here. This is the important part right there. What's V1I? Object number 1 is moving at 10 meters per second. M2 is, whatever it is, doesn't matter. What's V2I? What's V2I? What is it? 0. Yeah, why isn't it 15? It says 15 on the picture. Yes, it's relative to the x-axis. We're dealing with the x-axis, and when we look at this diagram, object number 2 isn't moving on the x-axis. As far as the x-axis is concerned, it's at rest. So we're going to say it's 0. Okay, MVF, solve for VF. Okay, what about the second one, the y component here? M1 is whatever. V1I is, what's the value of V1I here for the y component? 0. Look at it this way. How much of that 10 is up or down? It's all horizontal, right? So none of it is up or down. So we're going to say that M1 V1I is 0. M2 V2I is going to be 15 equals MVF. We haven't changed a thing. When we analyze problem number 1, we did it this way, get VF. When we analyze problem number 2, we did it this way and got VF. When we analyze problem number 3, we did it this way and this way and got 2 different VFs. Now, what do you think we're going to do with those 2 VFs? Yeah. Before we use the Pythagorean theorem, we're going to draw ourselves a little picture called a vector diagram. Okay, V1F would be a positive something. V2F would be a positive something. And then we combine them, and we get something like this. Now, you're suggesting that we use the Pythagorean theorem now? We can do that. Okay, we know what x is, we know what y is, solve for v. And we could also find the angle there using a little bit of trigonometry, right? So what have we done here today in a two-dimensional problem, one of these T-bone collision questions? Well, we've done a problem like this that we've done many times before. We've done a problem like this that we've done many times before. And then we've done a little vector analysis here that we've done many times before, not in physics 30, but we've done in physics 20 lots, right? Draw the vector diagram, do the Pythagorean theorem, and so on. Does that make some sense? Momentum is conserved no matter what axis you're on, x, y, or otherwise. Momentum is conserved. So use that. Okay, break it up into x and y and treat it as 2 separate problems. Don't make it harder than it has to be. If you can do this and you can do this for these 2 problems, then you should be able to do them for this problem down here. And then this part is easy, right? That's physics 20 stuff. Hey, let me give you a tiny little bit of notes here, and we'll see if we have time for one example here, okay? So the first line says that when you're analyzing a collision or explosion, that should say or, not of. A collision or explosion in 2 dimensions, what you want to do is break the problem up into 2 separate problems, the x and the y, and then recombine them. Right? Here we broke it up into the x, here we broke it up into the y, and then down here we recombine them using the Pythagorean theorem and some trigonometry. When you're analyzing the x component like we just did, you ignore the y component. So let's go back here again. You're analyzing the x component right here. Well, the y component was 15, but we ignored that. We pretended V2I was 0. We ignored it because we were focusing only on x. Similarly, when we were analyzing the y component, we ignored the x. spelled wrong again. It should be ignore any x components. Then you've got to recombine them. The Pythagorean theorem, which you learned about years and years ago. And a little bit of trigonometry, usually the tan function or the inverse of the tan function. Let's take a look at a sample problem here now that is pretty much like I described for you before you wrote down your notes, but this time has a little bit more detail to it, more numbers to it. Now, there is a couple things that I want to point out before we actually begin this question. The first thing is the 270 degrees thing. What is that? 7 meters per second at 270 degrees. We don't really have to know this notation in Physics 30, but I'm going to show it to you because some of the questions we'll uses that notation. If we look at an XY axis here, this would be 0 degrees. This would be 90. It would go around counterclockwise. 0, 90. This would be 180 degrees. This would be 270 degrees. So if the quarterback is moving at 7 meters per second at 270 degrees, the quarterback is moving this way, straight downwards. That make sense? His mass is 90 kilograms, or her mass is 90 kilograms, moving at 70 meters per second. Now, this person is tackled by a 110 kilogram linebacker running at 0 degrees. 0 degrees, you can see, would be straight to the right here. So we're going to make that object number 2. His mass or her mass is 110 kilograms, and the velocity is 8.0 meters per second. Now, we want to find the velocity at the center of mass of the combination of the two players. The center of mass is where the mass can be considered to be concentrated for both of them. In other words, we're going to pretend that they stick together and go off as one object. Even if they don't, that's okay, because the center of mass would be where the two of them would go off together if they did. So basically, we're looking for this right here. What's the velocity of the wreckage, if you want to call it that, of these two guys hitting each other? Now, you know what you got to do. You got to break this up into x's and y's. Okay, what you want to do is visualize this as two separate questions. An x question, where object number 2 is what we're focusing on, and a y question, where object number 1 is what we focus on. We say pi equals pf. We say m1 v1i plus m2 v2i equals, we'll call it mvf. m1 is 90 kilograms. What's v1i? What is it, Adam? v1i, I thought you said. Okay, so what's v1i? For the x component. How much of that 7 is across x component? How much of that 7 meters per second is this way? Anybody have that answer for me? 0, none. So we're going to say this is 0. M2 is 110. V2i is 8.0. The combined mass is going to be 200. Multiply that by VF. Let's say 110 times 8 is going to be 880 divided by 210, or by 200, is 4.4. Is that right? Okay, let's do the same thing for the y component now. Let's say pi equals pf, m1 v1i plus m2 v2i equals mvf. M1 is 90 kilograms. What's v1i? 7? Well, how about negative 7? Because it's downward. This is 0 because it's all on the x-axis. 200 times VF, that's going to be negative 630 divided by 200 is going to be give me 3.15? Negative 3.15, I think. What are you going to do with these? Let's redraw it, right? 4.4 this way, 3.15 this way, and then we'll do the Pythagorean theorem and the tan function to find the angle. Okay? VF a squared plus b squared equals c squared to get this. The inverse tan of opposite over adjacent to get this. we'll leave it there today, guys, and we'll pick up there tomorrow, okay?